And so the way we discriminate between a covalent bond and a polar covalent bond is this electronegativity index. Okay, so what does this mean? So this is the electronegativity, I can't spell today, difference, because, right, that delta means final minus initial, okay? And this scale right here, I'm going to call that is the EN, man, oh man, I can't even spell the word index today. Index. So that's the electronegativity index, all right? And so the way that this works, okay, is if, let's say, we're forming a new molecule, all right? So for example, let's say we're making something like HCl, okay? And I'm just going to say an H bonded to a Cl. We won't worry about getting the Lewis structure yet. And so now I want to know, is this covalent, polar covalent, or ionic? Okay. Well, and all these numbers, by the way, it's like absolute value. So it doesn't matter which way you subtract it. You just want the absolute value. So if I say chlorine 3.0 minus hydrogen 2.1, 3.0 minus 2.1, that gives me 0.9. And look at that. That's somewhere in this polar covalent or mostly covalent. And I think most chemists would say HCl is polar, okay? So it's qualitative somewhat, this formula, okay? We're not going to sit here and calculate this for every single possible molecule and say definitively, oh, 0.9 means it has to be only covalent. You can see 0.9, it would be mostly covalent, but it's somewhere in between, right? But if I look at something like HF, 4.0 minus 2.1, that gets me 1.8, okay? And so that's definitely within the polar covalent scale, all right? And if we look at something like, I don't know, potassium chloride, for example, okay, 3.0 minus 0.8, that's 2.2, right? That's putting us into the ionic scale. And we kind of know from our previous stuff that we've been learning that potassium chloride is definitely ionic. So we should use this scale, we should tread lightly when using this scale. And I think the most important to recognize is we go back to our standard discussion, right? Our standard definition of ionic and covalent. We make covalent compounds with we make covalent compounds, right, with all nonmetals, okay? Whether it's polar covalent or covalent, all nonmetals, it is covalent, okay? And obviously, if the nuclei are different and very far apart from each other, like hydrogen and fluorine, okay, or hydrogen and oxygen, right? If they're way on opposite sides of the table, it's going to be polar, okay? But if they're right next to each other, like something like a carbon and a nitrogen, right? Or, even something like an oxygen and a fluorine, if they're right next to each other, they're probably not far enough apart on this electronegativity scale to be full-on polar covalent, so they would be mostly covalent, okay? And the important thing to note here, the electronegativity, just like our other periodic trends, we should have a general view of how it works. And you can see there's a general increase when we go up, right? Francium at 0.7 all the way to hydrogen at 2.1. So that's a general increase, okay? And we see a general increase as we go across the table. And so really what electronegativity is, it's the, I should have had a definition here, it's the ability of an atom to attract electrons to itself. The ability of an atom to attract an electron to itself. Biggest takeaway, or, well, there's several big takeaways here. An important takeaway, fluorine is the most electronegative atom. Francium is the least electronegative atom, okay? And so when we think about this, this is very much connected to what makes a good reducing agent and what makes a good oxidizing agent. These things up here, oxygen, fluorine, chlorine, these are all excellent oxidizing agents because they induce a loss of electrons in other atoms. In other words, it's like saying they attract electrons to themselves. They're bullies for electrons. They're electron hogs, okay? So moving along. So if we were to now look at the electron distribution in these compounds, we can also see another kind of scale, another somewhat qualitative scale that gives us this idea of covalent, polar covalent, or ionic. And you can see right here with two chlorines, the nuclei are identical, okay? And in this electron distribution, you can see it's mostly in the kind of yellow-green area, all right? Which, you know what I mean? Like you see some kind of green on the outer edges right there, right? Do you notice that? Well, what's going on with that? So we did the electron configuration of fluorine, or excuse me, the Lewis structure, but the Lewis structure of chlorine will look the same. Look, all of these lone pairs, okay, I'm gonna give you some instruction on how to come up with these structures soon, okay? All of those lone pairs create a ton of electron density around the chlorine. So that's why you're kind of seeing some of this yellow area, but some into the green, okay? And so now when you look at HCl, look, there's a big difference here, right? Okay, and so by the way, what I should have said is this makes a pure covalent because both chlorines are the same color, right? There's no difference between the two. But now when you look at the HCl, this H is like kind of in the neutral area, but this chlorine is centering around the -1. And that's because the Lewis structure of HCl looks like this. The chlorine is surrounded by all of these other electrons, but the hydrogen is not. That's what makes it polar. And I'm going to show you on the next slide a nice picture here. Okay? And then when we get to sodium chloride, there's such a huge difference between these two, right? Sodium is positive and chlorine is negative. That just makes it ionic. There's no covalent bond there. All right? So what is this polar covalent thing? All right? It's what we call a dipole moment. The key part of that phrase being pole. Like a magnet has a north pole and a south pole. Or in this case, like a battery. A battery has a positive pole and a negative pole. Okay? So just like I showed you with that HCl, right? The chlorine, because it's surrounded by all those extra electrons, is somewhat negative. And we also should recognize that chlorine is very electronegative, right? Chlorine is going to be a bully for all of those electrons. So not only is it negative because or is somewhat negative because it has all of these lone pairs, but also the two electrons in these bonds, I'm going to draw them like closer to the chlorine, right? We recognize that chemical bond means two electrons. The chlorine is kind of hogging them. It's pulling them in this direction towards itself. And so that's what gives HCl a dipole moment. And we draw the dipole moment by making a plus sign near what's more electropositive, and the arrow points to the area that's more electronegative. Okay? So now here's a little conceptual question. Which of these has the largest dipole moment? And this is the series of the halogens with hydrogen. So these are all acids, right? Okay. And by the way, we know that when we put, HCl, for example, into a solution, okay, HCl aqueous, we know that it does break up. It goes and does chemistry. That's what not these are referring to. These are actually referring to these compounds as gases. All of these compounds, HF, HCl, HBr, HI, in the absence of water, will be gases. So all covalent gas molecules in the absence of water. However, we should definitely recognize and remember our previous chemistry that if I put HCl into a solution with water, it does this, right? Okay? So just recognize that. So which of these is, I'm gonna write, instead of Cl, I'm gonna write HX, or the X can be the F, the Cl, the Br, or the I. So which one of these has the largest dipole moment? Okay. Well, it's definitely the HF. Hopefully you came to that conclusion, because as you can see based on this color scale, the fluorine is, more into this negative scale, and the hydrogen is more into this positive scale. Okay? And we should also recognize that this is the most polar, so it has the largest dipole moment. That's saying the same thing. The most polar has the largest dipole moment. We should recognize that that's true because, once again, fluorine is the most electronegative element, right? So when you compare HF to HCl to HBr to HI, HF definitely has the largest electronegativity difference. So that's going to mean it is the most polar, okay? And so where this polarity, where this matters is if now we have a bunch of random, let's say HCl molecules, okay? So suppose I've got a bunch of HCl molecules floating around, right, as a gas, okay? If I were to now put these molecules into an electric field, okay, put in electric field. So there's a number of ways I can do that. I don't want to get into those details too much. One of them certainly would be to put a large magnet, near all of these random molecules. They're all going to line up with their dipole moments. Okay, so they would all line up positive to negative, right? They would all just line up based on their dipoles, right? The positive and the negatives want to get together. So that's what would be a consequence of these dipole moments. There's a lot of other consequences of these dipole moments that we'll talk about as we progress through this material.